The purpose of this video is to go through the process of writing exponential equations based on real-world information. So it looks like we needed a little bit more support for writing exponential equations, so I'm going to go through this in a little bit more detail than you were provided last week. So the first thing here is the standard exponential equation is written in this form right here, y equals ab raised to the x power, where a represents your initial value and b represents your rate. So we'll get to the initial value in just a moment. The big deal here is b. B tells you a lot of information. So b is what determines if we have what we could call either an exponential growth or an exponential decay. So a growth happens if b is any number larger than 1. So that would be, in a word problem, saying that something has doubled or tripled or is increasing by a certain percentage or is growing by a certain percentage. In general, if b is larger than 1, when we sketch it, we create something that looks like this. So that would be an exponential growth. And so in your problems, when you're asked to sketch, whether it's a growth or a decay, that would be what you create on your sketch. And the second thing that could happen is we could have what we call an exponential decay. So a decay happens if our b value is somewhere between 0 and 1. If our b value is between 0 and 1, that means that, as it says, we're decaying, we're losing value. Another common example is with half-lives. Just any kind of loss represents a decay. So an exponential decay is a horizontal reflection of a growth. So the way you would sketch a decay would look something like this. So once again, if you are asked to create the sketch, that would be the shape that you would make. So the next thing is, just a little recall back to what we were talking about last week. The b value is always with respect to 100% when we're talking about percentages, but we don't actually write that percentage. Instead, what we do is we're going to convert that that percentage into a decimal equivalent, which just means that you move your decimal 2 units to the left. So what we're going to do is we're going to take a look at a few examples, describe both their growth or decay, and then talk about the b value and as well as the percent change. So you're asked to determine the initial amount for this problem. So for the initial amount, remember our exponential equations are modeled by y equals ab raised to the x power. So our initial value is right here. So our a value, the initial value, is 100. Next thing we're asked to do is determine if this is a growth or a decay. In our case here, this is a growth. The reason why we know it's a growth is because our b value, which is 1.5, is greater than 1. So that means that we have a growth. Next thing you're asked to do is determine the rate of the growth or decay. So our rate is our b value. So we know our rate already, which is 1.5. And last thing you're asked to do is to determine your percent change. So remember, your percent change is how much did we add or subtract from 100%. So if we are at 1.5, sorry, let me write this, the percent change, which I'll represent with delta percent. Remember, delta is a Greek letter that means change in math. So our percent change is going to be that 1.5 that we got. And if we move our decimal 2 units to the right instead, that's going to give us 150%. So we're at 150% right now, but how much did we change from 100? So to get our final answer, this one's a pretty easy one to see. We are 50 greater than 100, so our percent change would be 50%. Okay, so we've gathered all our information. We knew the initial amount. We knew that this was a growth. We knew the rate, and then we knew the percent change. All right, what I want you to see if you can figure out, you might want to pause the video before I go over the solution, but take a look at that next example, try it out, and let's check and see how you did. So our initial value, which is a, is 20. This is a decay. The reason why we know it's a decay is because our b value is between 0 and 1. Next thing we know, our b value obviously then is 0.25. Okay, and here's the tricky part, our percent change, or a change in our percent. This is 25% if I'm thinking about 0.25 as a percentage. Okay, but the question is, how much are we changing from 100? So to get 100% and turn it into 25%, that means that we had to take away 75%. All right, next up, we're going to take a look at some given information. We're going to turn that stuff into equations. So the next three examples will follow that type of a format. Remember, A is the initial, so this tells me A. If I'm being told this is a growth or a decay, that means I'm going to add to my 100%, and then we are told at the end what we're going to change our percentages by. So first up, our initial amount is 70. So that means if I'm writing the equation y equals, our initial amount is a, which is, sorry, let me write the equation first so we all are on the same page here. Given the equation y equals ab to the x, my initial amount is a, so we're going to say y equals 70. Our b value, we're going to have to do a little bit of work. So we know this is a growth, so we're going to take our 100%. And if it's a growth, we're going to add the 2% we've got, which is 102%. But remember, we're not writing percentages, we're writing this as a decimal value. So we're going to take our decimal point and move it 2 units to the left. So that would give you 1.02 as your b value. So that means our b value is 1.02. And that would be raised to the x power. All right, here's what I would like you to do next. Same as with the other example, I want you to take a look at the next two, see if you can figure out what those are. You might want to pause the video here. When you're ready to go, press play. And let's check and see how you did. So this first one, our initial value is 125, so we're going to say A is 125. This time we have a decay, so we're going to subtract 10% from 100%, which gives us 90%. So if we know we have 90% as a b value, that would be 0.9. So we know we should have 0.9 raised to the x power. And the last example, we are told we have the initial amount of 500, so we're going to say y equals 500. This time we have a growth. We are adding 500%, so 100% plus 500% is 600%. To write that as a decimal value, we're going to write 6. So we're going to say 6, and this is raised to the x power. So that would be writing equations if you're just given general information. Okay, we can apply the same principles here when we're given real-world scenarios. So let's take a look at 2 real-world examples and see how that would look, and then we'll just also generate a sketch for good measure so we can visualize what's going on. So our last 2 examples here. Computer valued at $6,500 depreciates at a rate of 14.3% per year. Write an equation which models, word models isn't there, oops, the computer's value after 2 years. So it says the computer's depreciating, so the word depreciate always means to lose value. So we know the initial, so the initial is the 6,500. And we know the rate at which this is happening. So it's losing 14.3% of its value. So the question is, what is the remaining value that we've got? So let's calculate that real quick. So again, we're always doing this with respect to 100%. We're going to subtract the 14.3%. So when you do 100% minus 14.3, that should give you, I'm doing this in my head here, this is 85.7%. And when you move the decimal over 2 units to the right, that's going to give you 0.857. So we know the b value, we know the initial amount, so now it's just a matter of writing our equation. So this will be y equals 6,500 times 0.857, And instead of to the x power, this is saying after t years, so we're going to raise this to the t power. Okay, so for this last example, I want you to do the same thing we've done for the other ones. Take a read, look at it, see if you can figure out what the equation is going to be. Once you've done that, go ahead and press play, and we'll check your answer. So here's what you should have for this one. Population of a certain animal species is increasing. So keyword there is increasing at a rate of 3.58% per year. So for this B value, we're taking our 100%. It's going to be a little bit easier to do mentally. We're adding 3.58%. So when we do that, we get 103.58%. And then to convert that to a decimal, that'd be 1.0358. This 80 you have counted, that we're going to call that our initial amount, so we know what our initial is. So to write the equation, y equals 80 times our b value, which is our rate at which this is happening. So this will be 1.0358. And that'll be raised, once again here it says at the end, write an equation after t years. So we're going to raise this to the t power. And that would be our equation. So let's take a look at what these things would look like when we sketch them. So to sketch this, we will go ahead. For this first one, this was a decay. So if we were to sketch a decay, it should look something like this. Remember, this is the sketch here for an exponential decay. And the idea here is that as time goes along in the positive direction, the value of our graph, which is represented by the y, is decreasing, so it's losing value. Versus the second equation, we have a b value that is larger than 1, so that would be what we consider to be an exponential growth. So we should have something that looks like this. And again, the idea here is that as we increase the time, or as time goes along, the values for our y continue to increase. So that concludes part 1 of exponential functions. In the next portion, we'll take a look at what happens when we introduce a k value.